Alright, this is Pathways 4.24. We're to calculate several things. This again involves solution and the concept of molarity. I'm working another one of these problems because it's important to get this down. It's one of the key quantitative things from this chapter, okay? This solution stoichiometry, as I like to call it, which is almost always mediated, at least right now, through the unit of molarity. So it's good to practice this. So part A, this question asks us to calculate the mass in grams of the solute needed to make 475 milliliters of a solution which has a molarity of 5.62 times 10 to the minus 2 molar potassium sulfate. Now again, in the problem, they write out potassium sulfate in words. I just abbreviated that K2SO4 here, okay? I wrote the formula already. You need to have the ability to do that. I can't stress that enough. When you get to an exam and you see a name of a compound written out rather than giving you a formula, you got to be able to convert the word into the correct chemical equation. If you can't do that, on several questions I would anticipate you get stuck on the exam, okay? So really work on that skill if you're still struggling with it, right? It's writing formulas. So we want a mass here, ultimately, that's needed to prepare this particular solution. Okay, now thinking about how to get at that bit of information, right? Well, I remember, because I've committed to memory, that the number of moles of solid, regardless of what it is, can always be found for a solution by multiplying the molarity of that solution times the volume of that solution. If you multiply molarity times volume in liters, it's got to be in liters units, you get number of moles of solid present in that solution. Okay, so this is a really good thing because I know my molarity is 0.0562. I was told that in the problem, right? 5.62 times 10 to the minus 2. That's my molarity. And my volume is 0.475 liters. I was told 475 milliliters in the problem, but I know there's 1,000 milliliters in a liter. I divide by 1,000, move that decimal point 3 spots to the left, and get 0.475 liters. And I can very quickly then determine that this solution must contain 0.026645 mole of solid. That's that stuff that's dissolved up. Okay, so that's how many moles of solute here, potassium sulfate, must be present. Now after I ascertain how many moles of solid are present, all I need to do to get to grams, because that's what I want here, right? Mass in grams, how much mass in grams are there? All I need to do to convert to grams is a moles to grams conversion. Moles is the amount of substance. I just need to express it in different units, right? So let's think about how we can do that. So I'm going to rewrite this 0.026645 mole of my solid. Here that's K2SO4. I need to convert it into grams. So how can I do that? Well, if I know what the mass in grams of 1 mole of the K2SO4 is, I'm in business, right? If I look up the molar mass of K2SO4, I find that it's 174.26. I could, of course, also calculate that by adding up the parts from the periodic table. So I multiply 174.26, that's the molar mass of K2SO4, times the number of moles, and if I do that, I find that this solution requires 4.65 grams of solute, 4.65 grams of the K2SO4. Alright? So I can go grams to moles, moles to grams, ultimately to molarity if I have the final volume of solution. So these types of calculations, again, are really good to practice and get good at. Not only will it help you with this molarity concept, it's also going to help you just with general quantitative skills involved in this section of the class, which is pretty crucial, I think, overall. Now, part B. We want to know what is the molarity, that's the capital M, moles per liter of a solution that contains 7.25 milligrams of a solute, here that solute's calcium chloride, in each milliliter. Okay, so this problem's a little bit different. They tell us that they have a solution that they prepared of calcium chloride, and again, I think they used the words, I wrote the formula here. It's 7.25 milligrams calcium chloride. That's not very much. It's just a very small amount. You probably could weigh it out with a very good analytical balance, but it's a pretty tiny amount, and that's contained in every 1 milliliter. So this is essentially a concentration, 7.25 milligrams per 1 milliliter of solution. Now, that, as it turns out, is another concentration unit of measure that people might use. You could see that in a laboratory protocol, milligrams per milliliter. But here we want to convert that into another concentration unit, molarity. So it's essentially a concentration unit conversion, okay? So when I see this, I think about my definition of molarity being moles per liter. Molarity is not defined in terms of milliliters. So I said, well, okay, what if I just scale this up a little bit? What if I multiply everything by 1,000? What if I multiply all units by 1,000? So isn't 7.25 milligrams per milliliter essentially then equivalent to 7.25 grams per liter? All I've done is I've lost this milli prefix in both cases by multiplying both the numerator and the denominator by 1,000. So now I'm in grams per liter. So 7.25 grams per liter is physically equivalent to 7.25 milligrams per milliliter. It's just that this is a scaled down unit, and you can think of that one as being scaled up. Okay? But the cool thing about doing this conversion right off the bat is I've got my denominator now into liters. And I know from my memory that molarity, capital uppercase M, is what? Number of moles solute per liter. Of solution. Number of moles solute per liter of solution. You see that? Now, the cool thing about this is now our denominator are both in liters. And this is a mass base unit, 7.25 grams. If I could convert this number of grams to number of moles, I'd have my answer. And it's as easy as that, okay? So all I need to do is take this 7.25 grams and essentially express that in mole units, and I can plug that in the numerator of my fraction, and I'm set, I'm done, okay? As easy as that. So 1 mole of my solute, here that's calcium chloride, has a mass of 110.989. Space. 110.989 grams per mole for the calcium chloride. Again, just added up the parts to get that number. It's the molar mass of calcium chloride. So if I do the division with that, I find that I've got 0.0653 moles of solute. Here that's calcium chloride. That is contained in the 7.25 grams of calcium chloride. So if I go back to my equation, I can now write 0.0653 mole calcium chloride present in 1 liter. Remember back to this where I found there was 7.25 grams in a liter. All I've done is I've changed grams into moles. The amount of the fluid is still the same, okay, so that's still a liter. So sure enough, I have a number I divide by 1, which then obviously doesn't change that number mathematically. So I can say that my final molarity is 0.0653 capital M for molar or moles per liter. And I'm set. All right, so another kind of fun problem. There's one more. There's a part C here. Let's look at that. Part C. Let me go back to the textbook here and see what this one reads. Oh wow, this is a fun one. Look at this. It's the number of magnesium 2+ ions. Oh, goodness. In 1 milliliter of 0.184 molar magnesium bromide. So I've got an aqueous solution of this solid magnesium bromide dissolved up in water. The concentration of the solid is 0.184 moles per liter, and I want to know how many, if I were to count the magnesium ions that are present in 1 milliliter of this solution. This is kind of a pretty fun problem, I think, all right? Because it ties a lot of ideas about molarity, moles, Avogadro's number all together, okay? Now, obviously, we're not going to be able to count how many are there, but we want to estimate based on mathematics, okay? How many should be there. Now, I know the information that we're given is 0.184 mole per liter. Right? That's our molarity. And again, I've been harping on this, but if we multiply times the volume in liters, the molarity unit, or the liter units cancel, and I'm just left with moles. Okay? Here that's going to be moles of MgBr2. The question is, okay, well, what volume to use? Now, I'm curious about how many magnesium ions are present in 1 milliliter. It's not a liter, that's just a milliliter, which is 1,000th of a liter, 0.001. Everybody see that? Hopefully so. So then in 1 milliliter, I've got 0.000184 moles of magnesium bromide present. Okay? Now, I don't necessarily want to know about magnesium bromide. I only am asked about magnesium here. So how do I deal with that? Well, I know I have this many moles of the magnesium bromide. Can I convert to moles of magnesium? I think I can, right? And the way that I do that is I look at the formula for that compound, the MgBr2. For every 1 mole of my MgBr2, I've got 1 mole of magnesium ion. Now, if I was talking about bromide, it'd be different. There's 2 moles of bromide per 1 mole of magnesium bromide. But for magnesium, there's a 1-to-1 ratio. So that basically tells me then that the same number of magnesium ions are contained in that volume, that 1 milliliter volume, 0.000184 moles. So think about what I've computed right now and reflect upon it. I've now determined the moles of magnesium ions that are present in 1 milliliter of this fluid. Now, I wasn't asked how many moles of magnesium ions are present. I was asked how many if I were to count them, right? So hopefully you can kind of see where we're going with this by now. Can I go from moles of a material into a number count? Is there a way to do that? I think there is. I'll block you for a second here to keep the suspense. Ah, voila. It's the Avogadro number relationship. We know that 1 mole of anything corresponds to 6.023 times 10 to the 23rd of that ion. So if I take the number of moles of ions that are present in the 1 milliliter and I multiply it by this number, because that corresponds to a mole, I can convert to number count. And if I do that, I get 1.108 times 10 to the 20. That's how many ions are present in 1 milliliter of this solution. All right, so that was a really fun problem because it really connects a lot of ideas together. If you can get good at these types of things, this molarity concept, you should have down.